the go-green star-forming galaxy main sequence at redshift 1 to 1.5. And of course, in these sorts of projects, there was a substantial contribution from a lot of go-green members, and I've highlighted them in green. So yeah, thank you to everyone who contributed. So the main goal of this project is to basically understand whether there is an environmental dependence of the star-forming galaxy main sequence above redshift 1. And to give a simple summary, I guess, of what we see below redshift 1 is a mix in the literature. There are several studies who don't see any trend in terms of clusteral field galaxies having a higher or different star-forming galaxy main sequence, whilst others see a modest trend whereby field star-forming galaxies tend to sit higher. They have higher star formation rates at fixed stellar mass than in the field. And as Michael mentioned in his first talk, one of the main goals of Go Green is to, if we're extending to higher redshift above redshift 1, galaxies are significantly younger, have higher star formation rates, lower depletion timescales, which should allow us to place constraints on galaxy quenching and formation timescales. And while there are pioneering studies above redshift 1, to have this sort of large sample that's been relatively homogeneously selected galaxies to do this environmental dependence study, Go Green is perfect for that. So first off, I'm going to talk about how we measured O2 and how we defined galaxies that have that are O2 detections. So for each spectra, we basically fit two models, one assuming there is an O2 emission line and one without. We used Bayesian information criterion to help us with the model selection. And in general, we take a fairly conservative approach to this. We define an O2 detection as one where there's significant evidence in this Bayesian information criterion. There's a significant preference for a model with an O2 emission line. And the way that we calculate the O2 flux completeness limit is basically by binning all the spectra by O2 flux and finding the flux at which 80% of those spectra, an O2 emission line is detected 80% of the time. So this is an example of the O2 flux versus redshift. You can see the galaxies are color-coded by this Bayesian information criterion. So in purple, we have the sort of strongly favored detections. And the dotted line or the dashed line there is basically where our O2 flux limit came out. So in our sample, everything above that line in purple, we count as O2 detections. And very briefly, the way that we convert these O2 fluxes to star formation rates is by using a Gilbank relation, which includes this empirical correction derived from H alpha to correct for the metallicity and dust dependence of O2 luminosity on star formation rates as a function of stellar mass. And while this relation from Gilbank was derived at low redshifts, there are some works that do give some evidence that, at least to say redshift 1.5, there should be a relatively decent correlation between O2 and H alpha up to those redshifts. So one of the things that I should mention is that we used the 11 most massive Go Green clusters for this study. And the way that the membership was defined in terms of which galaxies are in the field and which are in the cluster is based off of the galaxy dynamics. And I'm not going to go into detail because I think Andrea Biviano is giving a talk on that tomorrow. And you can see the cluster and field redshift and stellar mass distributions of the O2 detections here. And as you can see, there is obviously quite a difference between cluster and field distributions, both in stellar mass and in redshift. So as our main goal is to measure the environmental dependence of the star-forming galaxy main sequence, we wanted to make sure we were controlling both for redshift and stellar mass. So we bin everything by stellar mass. And for redshift, we basically apply a correction to the field star formation rates based off of the difference between cluster and field redshift, using the observed cosmic star formation redshift relation for field galaxies from Schreiber et al. 2015. So hopefully that should basically take out any biases that would occur because of the different redshift distributions. And in our sample, we have 109 cluster galaxies and 202 field galaxies across these 11 cluster fields, redshift 1 to 1.5. I want to say here before I talk about the results that, so we published the paper a couple of months ago, but upon doing some more work for the data preparation, one of the things that I noticed is that I was applying a ratio for flux calibration of the spectra based off of the photometry incorrectly. I was multiplying rather than dividing by a ratio. And because of the nature of the GO green and G-class spectra, this basically ended up meaning that the sort of average star formation rates were very similar. It wasn't very obvious in the plots. However, the scatter was reduced. So basically all the results I'm showing right now are updated from the paper, and we're going to be doing an erratum to update it, but the trends are relatively the same, just with weaker significance. So keep that in mind. So this is the star forming main sequence, redshift 1 to 1.5. In red, they're the cluster galaxies, purple field galaxies. The two lines here are basically the star formation rates as a function of stellar mass, based off of our 80% completeness limits. The higher one is for redshift 1.5, the lower is redshift 1.0. And as you can see, there's not a huge difference in the field versus cluster star forming main sequence. There is a modest difference where for the majority of stellar masses, the field galaxy star formation rates are higher than the cluster. And this is about a 2 sigma difference, relatively modest, like I said. And this is an agreement with some works. For example, I think it's Navarro et al. 2018 with the Carla sample. They found, I think, a slightly bigger difference than we did. However, obviously some works, for example, Zeman et al. 2013, based off of H alpha at redshift 1 to 1.5, they don't see much difference. But even so, we see this modest difference. This does allow us to place certain constraints on different models of galaxy formation times and galaxy quenching. So in the paper, we explored a few simple models, and I'm going to show a plot from one of them. So if we say that, okay, the observed slight suppression in the cluster star forming galaxy main sequence is basically solely based off of cluster galaxies being formed earlier than the field, how far behind would they have to be in terms of times? How much earlier would they have had to be formed than the field? And to do this, we basically play around with the observed cosmic star formation relation versus redshift and the observed difference that we see. And we find that depending on the stellar mass, we'd need differences of around 0.3 to 0.6 gigayears to reproduce the slightly higher field galaxy star forming main sequence that we see. And if we consider an alternative scenario where cluster and field are produced at roughly the same time, however, we want to understand what sort of implications this has for quenching timescales. For example, in the delayed and rapid quenching model of Wetzel et al., where a satellite falls into a cluster and for a certain period of time, a delay time, the star formation rate evolves like the field would. However, after, there's this fading time defined by tau within which the quenching is more rapid. What do our observed results constrain in terms of those quenching timescales? So I should mention this is still in progress. This plot is taken from the paper and with the older sample, but I'm still working on reproducing that for the results we have now. But basically, what I think is that this plot will be similar, but with weaker constraints. But one of the things that we can see with this modest suppression is that delay timescales are basically constrained to less than around 1.1 gig a year. And for really rapid quenching timescales, the constraints on the delay time is even stronger. Yeah, so I think that actually brings me to my summary faster than I expected. That we use this homogeneously selected cluster and field galaxy samples for 11 of the Go Green fields. We wanted to know what the star-forming galaxy main sequence looks like at this epoch. And basically we see a very modest suppression for the cluster galaxies. And if we try to explain this as, okay, cluster galaxies are formed further back in time, we would need to see differences of around 0.3 to 0.6 gig years. And quenching timescales based on these observed differences are still to come. Yeah, I think that brings me to the end. Thank you for listening.
Thank you, Lyndsay. So that's great. That's actually got us a little bit ahead of schedule.